All right, so I'm just checking my Zoom settings here. Zoom. All right, so this is not helping. I'm going to turn off the record today. Great. Oh, right. Just checking the audio recording settings and then let a bunch of people in. Share. Is the lecture recording useful?
Yeah.
Oh, okay. So you guys actually refer to it? Nice. Okay, that's good to know. Sorry?
Favorite TV show.
One of my colleagues, when her husband passed away, she was not able to sleep at night because she's used to having people around. So eventually she turned to my my lecture recording just to have some background sound. And then that really helped her to sleep. So that's one unexpected use of my lecture recording, is to help people to sleep, which I have observed in my classes. It's like, it's okay. I do not feel offended whatsoever because I have done my fair share when I was a college student. So it's only fair that I do not get offended at all. Let me see. I'm just trying to make sure that I got everything set up. The screen recording is automatically turned on as soon as I have screen share, and I verify on this side that I do have screen share. I got every person in. Oh, okay, maybe not. One more. All right, so. Oh, there's one more. All right. Okay, so I got stuff ready and I just need to find all my stuff. There we go. There's one. Okay, so this is how ugly the resolutions got, for the first part of the question. So my question is, did someone take up on my offer of just writing a program to do it? Nobody.
I used a program.
You used the program?
Yeah.
Did you do the resolution of the program?
Yeah.
Okay. Did you write the program?
No.
Okay, that's not going to help because the exam is going to be on paper, so that program won't help you in the exam.
Unfortunately, I don't have a ChatGPT neural implant yet.
A neural link is a Bluetooth device, right? Yep, you have to make sure you pair to the right device now. So anyway, I will go through this process a little bit, and then at some point, I'm gonna say, okay, this is tedious, okay? It is extremely tedious, but at the same time, it's kind of like, hey, this is the kind of stuff that we can use a triple loop to do. So we'll go over that at some point.
So on the exam, will it be this complicated?
No, it won't be.
Okay, because I was like, I'm about to run out of time.
Yes. Anyone is going to run out of time in this kind of tedious test. All right, so what I'll do today is I'm going over part of the solution of the homework assignment, and then I'll move on to exam 2 from the previous semester, because exam 2 from the previous semester also has questions like this, but they are much simpler, with fewer variables, and things are easier to work on. So, I'm going to use that also as an opportunity to talk about this. But I do want to talk about how to convert from line 1. So line 1 is representing the proposed theorem or an expression that I want to see if it is implied by everything that is known to be true. Are we doing okay so far with what phi is representing? Okay, so the second line is basically going to go, it's going like, okay, what if we negate the expression that we want to check if it is a theorem of everything that is known to be true? So we have to negate the entire thing. So now it is just, step-by-step derivation all the way to the end. So everything is documented because, I have to be able to track my own work to make sure that I did not make a mistake. So this one, going from line 3 to line 4 is using the definition of implication twice. So once is applied to this particular implication, turn into a negation followed by a disjunction. And the other second time is the nested or the upper level implication of this particular implication. And I also do a negation. So one thing I also want to know is, did you guys find an editor that performs parentheses matching? Okay, so some people use VS Code, Sublime. I use Vim, Repla, Notepad++ probably can also do parentheses matching. So that helps a lot. This is not something that you want to do on a piece of paper. So
More like a whiteboard.
yes, a gigantic whiteboard. Yes. So the thing about having parentheses matching, I'm pretty sure you guys can see it too, is if I want to convert the implication, I know this entire thing is the left-hand side. So the parentheses really help to kind of indicate this whole thing needs to be negated. And then with the other implication, we have to negate this entire thing. So that's why having a tool that can do parentheses matching helps a lot. When it comes to De Morgan's law, the application of De Morgan's law, it is the same thing. This negation is applied to this particular disjunction. So we end up with not S and not R. And then when we apply De Morgan's law on the other side, it's the same thing. This negation is applied to this entire disjunction. So we ended up with the negation of everything in the original disjunction, but those items are now connected by a conjunction. So we still do okay so far with up to line 5. So from line 5 to line 6, it is also De Morgan's law. So this time the De Morgan's law is applied to this particular negation. So with parentheses matching, I can now find out, oh, okay, I'm applying the negation to a or. So in other words, this negation here is not is applied to this particular or over here. And as a result, I negate each individual component, change the or into an and that's the application of De Morgan's law. And then I apply De Morgan's law again. This time it is applied to this negation, applied to this conjunction. So and I ended up with not S or not R. So it is redundant, but at this point I'm not simplifying just yet. And then I use associative law to dissolve parentheses. Now that is really useful. That's also very important. All right, we got a whole bunch of people doing remote participation. All right, so on line 8, we are using associative law because what I did was I removed unnecessary parentheses. Okay, that is actually really useful because now I know P, not R, not Q, not S, not T is one single conjunction. Okay, so that is important because otherwise, I would look at this and go like, okay, am I having two different things? Should I apply distribution or not? Yep. Associative law. It means the removal of parentheses. Okay, so let me illustrate what associative means. So A or B or C is the same thing as A or B first and then or C. So normally when we write it, we do not need to use any parentheses because how you group the application of the operator does not change the output. So in this case on line 20, this plus here applies as a disjunction, but it also applies as just addition in normal algebra. So that's called the associative law. When you look at C and C++ operators, depending on which operator you're looking at, they can be left associative or right associative. In other words, certain operators only associate on this side when you do not specify the parentheses. Others will apply in the opposite order, opposite direction. I'm trying to remember which one is which one. So with assignment operator in C and C++, it is right associative. In other words, when you have, okay, I'm just going to use this as an illustration. So when you have A equals B equals C in C and C++, okay, it is the same thing as A equals to B equals C in that particular nesting of parentheses. On the other hand, the less than and the greater than, I cannot remember the technical name of those operators. When you use C in and C out, those are specifically left associative. So when you say, okay, when you say C in to I to J to K, this is really the same thing as is the same as in 1, 2, 3, C in to I, then to J, then to K. So the reason why that is the case, I know I'm getting a little bit out of scope here because these are topics that should have been covered in CISP440, not even 400. Did you guys get this part? Yes? Okay. So the reason why it is left associative in this case is because the operator returns the stream itself. So that means the stream can now apply to this operator, and this whole thing returns the stream again, which is then used for this particular operator. The other way around won't work, because if you associate it the other way around, then it will first read into K first, then it will read into J, then it will read into I, which is the opposite order of what we expected to happen. But for assignment, which is on line 22, it has to be right associative. Because what happens is whatever C evaluates to, it will be used to update B. Now, normally in most programming languages, assignment is not an operator, it is a statement. In other words, it can only update one thing at a time. But in C and C++ and all the languages derived from C and C++, assignment is an operator. So that means assignment itself returns a value. The question is, what is it returning? It is returning the value that you use to update the variable first, right? So now the value of C is also used to update A, because E equals C, or the assignment of E equals C, returns the value that you use to update variable B, which is then used to update variable A. So that's why, whether it's a right associative or left associative operator does matter in C and C++. So I'm not sure whether this is making any sense. Is that okay? I mean, okay. So it is a little sidetrack compared to what we are doing here, but it is nonetheless, I think it's an important point to go over. All right, so between line 8 and line 9, we did some simplification, getting rid of the double negation. And then from here to here is distribution. So this is where distribution can happen. So when you want to apply distribution, okay, so let me describe distribution here. So distribution is A and B or C is the same thing as A and B or B and, A and C. Now this is one distribution, but there's also the opposite, which is A or B and C can also be re-expressed as A or B and A or C. So there are two distribution laws in Boolean algebra. In normal algebra, only line 22 applies. But in Boolean algebra, line 24 also applies. Is that okay? So in all of these examples, A can be an entire expression. It can be a single variable, but it can also be by itself a complex expression. Same thing with B and C. They're simply placeholders So that means when you need to think about which rule is applicable, you need to abstract the whole thing and go like, okay, I'm treating this entire thing as one thing. I'm treating that entire thing as one thing, and these two are ORed together, and then the entire thing is ended with that huge thing over there. So you have to be able to identify these things, syntactically, structurally speaking, you have to identify the overall structure. Is that okay? All right, so let's move on then. All right, so we got to the distribution and then we get to simplification again using associative. So what this means is the extra parentheses here are not needed because we have a OR here. But then what are we doing with the result of this OR? With another OR. So all the ORs can be combined, so the parentheses get dissolved. And then we have De Morgan's law again. So in this particular application of De Morgan's law, this negation on the very outside of the left-hand side is moved to the inside. Actually, I take it back. This negation applies to the entire expression. Let me show you the parentheses. This is why, having parentheses matching is really helpful, because now I can show you that this negation applies to this expression. You can see how the purple highlight is marking the end of the start parentheses. So that means we're negating the OR in the middle. So that means when we apply De Morgan's law, we end up with the negation of each component. This is one component, and this is an AND with the other component over here. And then we apply De Morgan's law again. This time, it is applied only on the right-hand side. So this knot of this bunch of AND is, we apply De Morgan's law. So we end up with the negation of every component of the original conjunction, but now they are in the disjunction. And then we apply De Morgan's law again on the other side. Oh, okay, I guess, I just did a copy and paste without actually doing anything. So we can take out one. Okay, so here I remove the unnecessary parentheses. In other words, the outermost parentheses are really not needed anymore. It doesn't do me any good. Originally, I have a negation on the very outside, which means the overall pair of parentheses are important, but now they're not important, so I remove those. And then we apply De Morgan's law again. So this time when I apply De Morgan's law, it is applied to this negation, to this particular OR operation. So we ended up with the negation of each component ended together this time. And then we apply De Morgan's law to each individual one. So this negation of this AND ends up with this disjunction. This negation applied to this AND ends up with this disjunction. And this particular not applied to this particular AND ends up with this disjunction. Are we still doing okay so far? All right. And once we get here, we just have to remove the extra parentheses, which is this particular pair, which is highlighted right now. And then we end up with the C and F that we need. Are we doing okay so far with all of this? Okay. So are there any questions about, the applicability of each particular transformation, each particular rule in Boolean algebra? You can refer to a line number, you can refer to, like, I'm not sure what happened between this line and this line. Looks like we do not have any questions. Yep.
Pretty sure I know the answer, but like on lines 21, 23, the distribution laws. If you distribute a negated value, you don't need to do anything with the Morgan's law, right?
Okay, say that one more time.
If you distribute a negated value, like if it's not A that you're distributing, you don't need to do anything with the Morgan's law.
Well, if this is a not A, then you preserve the not A throughout the distribution. Is that what you're asking?
Yeah.
Yep. Basically, if you have a negation of something, you treat the negated thing as one thing, as A. Yep. You can also look at this entire thing from the perspective of a syntax tree in terms of the expressions. Okay, does anyone know what I'm talking about or have a vague idea? Nope, okay. So let me see if I can still use the tool that I had yesterday. So I'm hoping that I can still do this into view. All right, this is from yesterday. I'm gonna turn a new page or make a new thing, but I want to see if it still works because sometimes after a while this is not going to work anymore. So let me see whether it still works today. Yep, it still works. Okay, good. In that case, I need to run another command here. Fix the stylus coordinate system. This is funny. I have no idea where I put the stylus. I think I left it in Rave Hall. So I don't have a stylus to explain things today. In fact, I have to go back to Rave Hall to pick it up. I can only do on the whiteboard now, or I can do a pseudo thing, using text. I'm just thinking, huh?
Use MS Paint.
I can use my finger, what I'm losing is not the application. I still have the application. I lost my stylus, which is the way that I can write things on the screen. I guess I'll just do it on the whiteboard because, that's otherwise I have to spend a lot of time to make things work. So let me kind of switch back to the editor. Because I think this will help some of you understand when and how to decide which rule applies. Where is my editor? Did I exit out of it? Oh, I think I know what happened because I got too many tabs and the screen is really wide. It's a Lenovo stylus. Which also would be the same kind that you use for HPs. So if you have an HP stylus, it will also work. Nope. It's a Samsung, probably won't work.
It's a digitizer or something. Right?
Yeah, it doesn't work. Yeah, because there are a few standards of how styluses work. There are 3 big standards. iOS uses one particular one. Samsung uses one, which is, I think, the same as,
In video you while you're doing all the whiteboarding.
Okay, sure, that works. But I still need to get back to the expression that I want to use as an example. And that is difficult because I made my terminal too wide. So let me get it back to a more normal size. Nope, it's not that, not that. Is it this one? Nope. Nope. I cannot remember where I put, oh, there we go. Okay, excellent. So with this one, I'm gonna pick a particular place where I can apply distribution. So I'm going to pick this one, or I would pick, okay, I'm trying to find one that is kind of interesting to use. I'll use this one. So we are looking at this expression here, okay? So let me just use the cursor key so that we can focus on which expression. Okay, so this is the expression. So when I draw the syntax tree of this thing, what is the last operation? The root node of this tree is going to be the very last operation of what is in parentheses here. What is the last operation here? It's an and, right? So because you have this entire sub-expression ended with not t. Yeah, so the overall operation of what is highlighted right now is an and. So you have an and operation as the root node because the root node represents the last operation to perform. What is on the left-hand side and what is on the right-hand side of the and. So on the left-hand side, okay, in terms of highlighting the expression, we have basically not S, and then we have an OR. So that means we have an OR here. The last operation is an OR, and then we have the left-hand side and the right-hand side again. So I'm not going to do the simplification because I want to show exactly what syntax tree you should be seeing on line 8 with the highlighted expression. So we have a negation. Now, negation is not a binary operator. It is a unary operator, which means it only requires one single component. So what are we negating? We're negating another negation expression. And then that inner negation is applied to S. So on the other side, it is the same thing. So we have not of R, right? And then on the other side, we have the not of T. So this is the syntax tree of the expression that is highlighted on the screen right now. Is that okay? So what does this have anything to do with algebra? So the one thing it has to do, what it has to do with algebra is in terms of distribution, it's looking for the and the or relative to each other like this. That's all it's looking for. So what you're doing in terms of distribution is to look for a pattern like this, and then you're just converting it so that you end up with an or on top, and then whatever you are ending, okay? So you take this entire subtree, we'll call this subtree A, we'll call this subtree B, we'll call this entire thing subtree C. So what you end up doing is to do an and here, and then the and is going to take the subtree A, whatever it is, and end it with subtree C. And then on the other side of the or, you're going to end subtree B with subtree C. So you can take a picture or you screen it.
I'm on the video.
Oh, okay. So are we do okay so far with this? So once you look at this entire thing as a tree, it doesn't matter how simple or complicated subtree A is. It is just a single node from the perspective of the OR. And then the same thing applies to B and C. They're basically, each one is only seen as, oh, this is a node in the tree. Okay, take the entire node. And what we do is we replicate the subtree C so that it occurs twice, because we got two conjunctions now. And then we, on one of the conjunctions, on the left-hand side, we have A, and then with the other one, we have B. So are we doing okay so far with this? I mean, I can only talk about expressions as an expression tree because you are all taking CISP430 or have already taken CISP430. But this is, one way to kind of visualize, the applications of the algebraic laws, not only in Boolean algebra, but also in just about any algebra system. This is one way to look at things and understand, when can I apply which rule? Is that okay so far? All right. So getting back, to the screen here, the difficulty of doing something like this, just using an editor like this, is we don't get to see the operators in a tree. We don't get to see the expressions like a tree. So that means you need to have the experience to have worked with parentheses and stuff like that enough in order to recognize it's like, okay, I kind of get what this is about. And this is one whole thing. This is node A. This whole thing is node B. This whole thing is node C. And after I apply distribution, I end up with something that looks like this. So are we doing okay with this? All right. All right. So now that we have talked about, how to get to the CNF from the negated proposed theorem, we make a super CNF out of it. Okay, so this is a super CNF. So the way I work on this, okay, manually, is to do it very systematically, which may not be the best way to do it, but it's very systematic. So I look at the first variable of the first disjunction, and they go like, okay, what can this particular P, let me go back here. What can this particular variable P be used in a resolution? So the double caret, okay, over here is indicating, oh, this is the first negation of a P that we find in another disjunction. So now these two can resolve. So when these two resolve, what happens is I take the remaining portion of each one. So I take R from the expression where the blinking cursor is. And then on the other one, I also take R or not S or not T, from that one. So I end up with a new, I end up with a new disjunction, which is R or not S or not T. Yep.
You don't apply resolution to the second, not P either, too?
The second not P.
There's another not P.
You mean this one?
Yes.
Oh, in time. In time. So I do it, you're right. Okay, I forgot to do it on that one. Or did I?
Because when I was doing it this way, like, it
Mhm.
was getting ridiculous how long.
Yeah.
And I thought I was doing it wrong, to be honest. Like, I was like, there's no way this is right.
Well, the order of doing the resolution, does matter because in certain orders, especially if it does result to false in the end. In certain orders, it can be done like really fast, but in other orders, it would take you a long time. So this is why, so you're correct. I forgot to apply to this one. So if I do apply to this one, do I end up with something that's already in the system? Because I do not. Okay, so I did forget about this one. So doing this manually is prone to errors or omissions in this case. I move on to this R, and you can see how I use the carets, to kind of help me track, the resolutions. So by the time I get to row, 62 or line 62, I probably realize, this should be done with a program. So now the question is, if you do this with a program, how do you do it? How do you represent a disjunction? Because the whole thing hinges on how do you represent a disjunction? Because if you have a really handy way of representing a disjunction, that makes it pretty easy to do all the matches, right? So the question is, how do you do it? What is the representation of a disjunction? I can give you a hint, okay? So assume that the number of variables is given. In this case, we have 5 variables, P, Q, R, S, T. So what would you use as a method or a data structure to keep track of one single disjunction? Like P or R is a disjunction, not R or Q or S is a disjunction. And I flip the order. I really should have been more consistent with alphabetical order. So what would be the best way to represent a disjunction? What is the most general way to represent a disjunction when you only have 5 variables? You can use an array or a vector, okay? So you would use a vector of 5 something. The question is, 5 what? So some people would say Boolean, right? 5 bools. Well, that won't work. Because with 5 Booleans, then you can only represent whether a variable is negated or not. But you cannot represent a case where the variable is missing entirely from an expression. In other words, if you look at P or Q, okay, I'm gonna move the cursor up to what most of you can see. So if you just look at P or Q, what happened to, this is P or R, okay, I keep saying P or Q, but this is P or R. So when you look at P or R, what happened to Q, S, and T? They're not appearing here, right? So if you use an array of 5 Booleans, you cannot do it. So you have to use an array of 5 integers where you can have -1 representing something that's negated, and use a 1 to represent something that is not negated, and use a 0 to represent something that is not in the expression at all. Are we doing okay so far? All right. Because the other way to look at an expression like this one is to say, oh, where Q is supposed to be is a false. Where S is supposed to be is a false, and where T is supposed to be is a false. So if you keep, if you add all of these extra zeros, which mean absolutely nothing from the perspective of a Boolean expression, but those are placeholders, right? So now each one lines up and say, oh, there are 5 items in each and every single disjunction. The position tells you which variable you're dealing with. The first one is P, the second one is Q, the third one is R, and so on. So using that as a representation of a disjunction, how would you spot something that you can resolve it?
Matching the unsigned in technique.
Where you see a 1 in one position, you want to look for a -1 on the other side. Where you see a -1 in one, you try to look for a 1 on the other one. If you spot one, then that particular variable goes away. Everything that is a 0 does not appear. Everything that is not a non-zero from either of the expression would be concatenated, together. So now the next question is, after I do the resolution, what happens when one has a 1 and the other one has a -1, but that particular variable is not used for resolution? In other words, one has a not t, the other one has a t. And t is not being used for the connect as a connector of the resolution. So what do? So your end result ends up with t or not t, right? So what happens to t or not t? It becomes true, becomes a 1. And once you have one single 1 in the disjunction, the whole disjunction is 1. But a 1 inside the conjunction doesn't do a single thing. It is the identity. So you know that one is not going to be useful. So that's how you can match and see if you can create new expressions from resolution. And when you make a new expression, you have to check whether you have seen it already. Okay, how do we check that? I give you 2 expressions. How do you know whether those 2 are the same or not? Using the representation that I have told you already. You just go to each and every position and ask, is index 0 the same? Yes. Index 1, yep. Index 2, same. Index 3, same. Index 4, the same. And the 2 expressions are exactly the same, which means if one is the result of a resolution step, that step does not give you anything new. Does that make sense? So the entire thing becomes basically just a fixed number of nested loops. You don't even need recursion to do this. So I was kind of surprised. Huh?
So there's 3 loops.
I cannot remember how many because you need one loop, at the most. Okay, so the outer level. Okay, let's take a look at the pseudocode. So I know I'm talking a little bit out of the scope, but I think this is kind of important because this kind of stuff is related to CISP440, which is algorithm design, right? So we need an outer loop. Okay, the outer loop basically is saying, while not done, do the following. But done is very ambiguous. Okay, what do you mean by done? So there are 2 things that are considered done. So we have a or here. In other words, while no contradiction or found new disjunctive element, then we continue. So in other words, if you find a contradiction, you can get out of the loop. If you did not find a new disjunctive element from the previous, from whatever is inside this loop here, you can also get out because it's a dead end. So those 2 are conclusions from the application of resolution. If you do see a contradiction, that means you're done because the proposed theorem is indeed a theorem. If you get out of the loop because you fail to find a new disjunctive element, that means you're hitting a dead end. There are no more steps that you can perform in terms of resolution. Yep.
So just to clarify, so for resolution, to reach the end, the first arrow,
Mm-hmm.
could that go on infinitely or does it have to reach the end of the CNF to be done? Of the
It
superintendent.
cannot go on indefinitely because the number, okay, so think about this, okay? Because remember what we said about the data structure to represent a single disjunctive element, right? So a single disjunctive element is something that looks like this, okay? You have, this, 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 this. Okay, so if you have 5 independent variables, then each data structure to store a disjunction will look like this because now you have P, Q, R, S, T, each taking one position in the array. But each question mark can only be a -1, a 0, or 1, because each variable can either be non-negated, it is in the expression, it does not appear in the expression at all, or it appears in the expression but negated. It only has 3 choices. So that means the total number of disjunctive elements you can have in the entire system, the entire space of disjunctive elements is how big in this specific case? How many possible disjunctive elements can I have? It has to do with 3 and it has to do with 5. The 3 is because for each position, there are 3 choices, and then 5 has to do with there are 5 of these. This actually goes back to counting, okay? Because we have 5 trials. Each trial has 3 possible outcomes. And it is with replacement, because when a variable is negated, the next one can also be negated, okay? Just because someone is already negated doesn't mean other things cannot be negated. So what would be the total number of outcomes in this entire experiment? I know I just shifted gear to talk about the accounting. We got 3. Okay, let me go back to use the pointer. So we have, okay, so we have 3 choices here. And then for each one of those choices, we have 3 choices here. For each one of the choices of these 2, there are 3 choices for this guy. So what do you think the tree is going to look like? Okay, so this is also going back to the tree construct. So when you look at the tree construct, okay, this is the starting point. The first variable has 3 possible choices, okay? It is non-negated, missing entirely, or negated. So, and then for P, okay, this is for P, and then for each version of P, you have 3 ways to go for Q. For each version of P and Q, PQ, you have 3 versions to go for S, R, okay, R first, and then S, and then T. So what do you think would be the total number of leaf nodes in this particular tree, assuming it is a symmetric tree, everything has a fan out of 3? 3 to the power of 5, that is correct. So that means our expression space, our, remember the space for the well-formed formulae? This time it is finite. And that's why it is nice, because if it is finite, even though we can keep doing resolution, like what you're seeing here on the screen, at some point, you are going to hit a dead end where you cannot discover any new expressions. And at that point, if you hit a dead end and it is not, you're not getting to a 0, that means whatever is being proposed as a theorem is not a theorem. Yep.
The combination of function and resolution to simplify expression.
I did not specify that in the homework assignment, but that would be a very good thing to do, okay? So if you apply absorption, along with the resolution, that can really, really help speed up things, right? Because in this case, now I did not specify that in the homework assignment, so I cannot assume people know that they can do it. But if you apply that, it's going to be okay. So you can see there's a not R here, right? All by itself. So that means everything that has a not R can go away. So how many things can go away at this point of all the steps? We got 1, 2, 3, 4, 5, 6. 6, okay, I missed 1, 7. Okay, I'm going to cheat. Okay. I am going to cheat because I can do this. So, yeah, so every single one of these, except for the non-R by itself, they can all go away. Yep,
So was there no, so was the first one, there is a theorem or there's no theorem?
the first one?
Yeah.
I cannot remember, frankly, I cannot remember which one is which one. Because the way I created the question is I have to come up with an expression where when you apply the negation of that thing and end it up it with the what is known to be true, it has to come to false for every single row. And I did create an expression like that, but I cannot remember which one. Yep.
Would it also work if you have P or not T? And you have P or not S and not P? Or not T?
P itself is already appearing by itself here.
Oh, yeah.
So everything that has P non-negated can also go away. So absorption can really, really help. Let me answer his question first. Go ahead.
Earlier you said, the order in which you, my resolution matters.
Yes.
Could you explain that?
Only when a contradiction is in the end. If a contradiction is not in the end, then it does not matter.
So you did it one by one for the resolution, but you can skip some if you like see like a certain way to.
Yes, you can. Yep. I prefer not to do it because, by skipping ahead means it's harder for me to later on. If it is not a theorem, if I skip around, then I can miss certain things and not know about it. Yep.
That's why I did the first one because there was so many. It was so long. Like, there has to be a rule.
So did anyone apply absorption, along the way? Okay.
So many.
All righty. So are we ready to talk about exam one? Okay, because exam one has elements like this too, if I remember correctly. Exam two, sorry. Yep, exam two. Yep.
This was that, it wasn't,
I cannot remember which one is which one. So I'm gonna have to go back and check my the key. But this is how I did it, kind of manually and, really, really systematically.
So again, my question, if you have R or not S,
R or not S, okay, so R, okay, hold on a second here. R or not S, okay.
right, so and you have it by itself
Uh-huh,
and you have it in the other.
yeah, the other ones can
Get
go
rid of
away. So if you have R or not S, then the one that only has R or not S still has to be here. Unless you find R by itself or not S by itself. But
Also,
until such time, then you have to keep R or not S by itself. But everything else that includes R or not S as one of its components, they can all go away. Yep, that's absorption. All right, any other questions? Yep.
So just going through the entire process though of the you're recording this, right?
Not at some props yet, but this is being recorded to Zoom and then I'll download it and re-upload it to YouTube. Yep. The what? Oh, okay, sure. So I can show you individual steps, okay? So I will, well, I can start with something that doesn't look as gnarly. Maybe. Okay, maybe this one here. Okay, we'll start with this point here. So on line 24, I am on the second disjunctive expression and the second variable of the second disjunction, which is a Q. And I'm basically scanning everything else and look for. I did not make a mistake because I switched the order between R and Q. So let me check. That doesn't make sense to me. I cannot resolve a R with a not R. Okay, okay, I think I know what happened. At one point in time, I switched the R and the Q. the ordering between those two. So this one really is referring to, I think we're still on the not R. No, this is on Q. Okay, so I am not sure what I did here. Okay, let me check.
You getting an RST?
Yeah, I'm getting an RST from the previous step. So I think these two and the result shows up here. Yeah, but they are not resolving the correct thing. Okay, so let me check my steps. Okay, the first step is correct. Okay, so this is still a good example because this P can find a pairing not P here. So these two expressions can resolve. Hold on a second. I see your hand. So this R is the remainder. This R or not S or not T is the remainder. So so I basically created a new disjunction, as a result of that. Yes, go ahead.
So did you already do the first P with the second negation P? Great.
No, this P is using this not P for resolution.
But after that, aren't you supposed to match it with the next?
Yes,
P?
systematically, we should do that. So that means, so what you're saying is we should match this P with this particular not P over here. And then the result of that resolution is going to take all the remaining stuff. So we have R from the first one, and then we have R again from the second one, which doesn't double count. So we have R, Q, S, T in this case. You're correct.
You did that late.
I probably did so. I cannot remember. So we can look for R, Q, S, T. So I did not do that. I mean, it remains not appearing as one of the resolutions. So I forgot about that one entirely. And this is why you're doing it, by hand has problems because, sometimes if you miss one, it's hard to go back and say, oh, I missed that particular one.
So, and then moving on to the next part, you're going to find the R, right? You kind
Say
of-
that one more time.
you're gonna leave it on, the R, here, R, right? And you can kind of not-
Yes. But at some point in time, I did a global replacement, between R and Q because they were out of order. So I replaced the ordering. And I think that kind of messed up, how things look, in the resolution steps.
So this is an example of something that does not,
I cannot remember. I cannot remember whether this one is supposed to be resolvable or not.
because I want to, what we want to look out for if it can collapse into a zero.
I think if we get to the practice exam, we might have an answer to that. I can show you one. Yep.
Okay, so the second line, the
Mhm.
last and then the one, like not before, but the one before that one.
Which line? Line number?
Oh, 36.
On line 36, like this one?
So the third to last and then the last and. Could you apply absorption to that? With those two,
Yes, you can.
so you can get rid of the.
Yeah, you can do it right away. Yeah, so this one can be absorbed into this one here. In other words, as you create more expressions as the result of resolution, you can apply absorption as well. So that will basically help control the number of expressions.
That's probably something I should have done.
Well, I didn't say that you guys should do absorption along with resolution, so it's okay not to do it. All right, anything?
How many lines of code?
How many lines
How
of code?
many- How many lines?
I do not know.
Scroll down.
Oh, this is not done yet. It's not even close. Yeah, it's not even close to done. I mean, look at this.
Where do you want us to stop?
What I really wanted you guys to do is just give up on doing this by hand and instead write a program to do it. I did say in the previous lecture, when this was assigned, that I would totally, be okay with you guys writing a program to do this. That was a hint. But do you feel you know enough about resolution now? I mean, I can just change the weight of the homework assignment, so it doesn't matter that much. I mean, that is not an issue. But did you get the exercise that you need to know how to apply resolution and know how to convert the negated theorem into a CNF?
For this, going over it, yeah.
Okay, well, then the assignment has done its job and I can just change the weight. If most people feel that this is like, oh, I cannot do this.
I don't know if this is an exam too, but is there a chance you could give us for one word to actually address results?
I think I have examples like that. Give me a second to retrieve those.
Just like a thing out there.
Yeah. Absolutely. It's probably the semester before the last semester. I have to search. Give me a second.
I think I saw one of the exams use the truth table to find this, you know.
Right. Right.
Which is much easier.
When you have
Much
limited variables, yeah, it really depends on a lot of factors. I think I lost track of my browser, so let me find my browser first. Yep, that's the one. Okay. All right, so I can go ahead and try to find one where it is resolvable. It's probably the one before, so it's going to be file / No, that's fine. I mean, we probably still want to, talk about the other, types of questions, but we have some extra time because typically what I like to do is to give you guys, give you a practice exam the week before the actual exam. But we are not having exam 2 next Wednesday because I won't be here on next Wednesday. So your exam 2 is actually on the Monday after next Wednesday. So we do have a little bit more time to talk about the rest of the questions. So I don't want to change context because you guys already have loaded, this entire context of resolution and whatnot into your head. So we'll just continue with this one and then we'll talk about the other stuff later on. You and then you, go ahead. So I'm going to pre-record a lecture so that way you guys can still kind of move forward with the content. As far as exam 2 is concerned, we have covered all the material. Today is the last day to cover resolution and whatnot. So we already have all the content for exam 2. So that means next Monday and also the recorded lecture on next Wednesday will be on new material that is not a part of exam 2. Yep.
Exam 2 covers discrete probability, right?
No, the exam 2 only goes up to resolution. So it starts with relations and then it goes into propositional logic and then up to resolution. Resolution is really the cheating thing of propositional logic, because we talked about propositional logic with all of those different rules, right? Simplification, distribution, the Morgan's law and whatnot. But the thing is, if you can express everything as a CNF, all we need is really just resolution. Now, from a human perspective, you guys go like, oh man, if I could use absorption, or if I did use absorption, I would have done this a lot faster. That is true. But from the program's perspective, once you have the super CNF, resolution itself is extremely mechanical. There's nothing tricky about it because every single time you just match, nope, match, nope, match. Okay, that works. Okay, remove the connecting variable, just kind of concatenate the rest, and you have the new expression if it is a new expression. If not, you go like, okay, that's not a new expression, keep going. So let me go back to CISP440, and this is going to be the one semester before fall. So this is spring 2022, and it is It's not showing up like this. All right, so I have to go look for the files. Give me a second here. All right, so we have X2. Okay, we do have a bunch of X2 thing. That was back in the pandemic days. So I had one question for each student. But I have to remember how I named those things. Nope. Did I get a path wrong? Choose. Yep. Okay.
Oh, you have two slashes after the file. Oh, great, yeah. Great.
I think it's supposed to be 3. I think it is supposed to be 3. Oh, because I need a tilde. There we go. Now we can find it. Nope. Oh, I think I know what. It's supposed. It's supposed to be home that. There we go. Nope. Did I miss? I forgot about the home again, didn't I? There we go. Okay. Home. Yes. All right. So we'll focus on this type of question. So the questions are here, 7, 8, and 9 are of that nature. So in this case, psi, everything that is known to be true is this. So the first thing you need to do is to convert that into a CNF. Okay, so let's do this. This is a lot simpler, right? I mean, look at this. So let's convert this into CNF first, and then we'll see what to do with phi. All right, so I'm gonna have to go back to the editor right here. All right, so this is psi, so we just have to convert it into a CNF. All right, what is the next step to convert this into a CNF? Definition of deficit. Yep, okay, so we will take this implication here, negate this side and turn it into a OR. So the way I usually do it is to do it like this. And then I just add a negation side and turn the implication into OR. Are we doing okay so far? This is the definition of implication. And then I do the simplification, okay? And then what do? We have the opposite of a CNF right now because we have a DNF, we have a disjunctive normal form. We do a FOIL, okay, very good. It's the distribution. So we have not P or not R, not P or Q, Q or not R, Q or Q. And then we can simplify a little bit more because Q or Q is just Q. Now, if you want to do absorption, that makes it super easy, right? Okay, so let's just test whether you guys know how to apply absorption. How do you apply absorption on line 103?
You have the Q. And you have the other thing, which is Q plus a bunch, anything.
Yep.
And so you can just get rid of the one that has the.
Yep, you're correct. So we just end up with a single Q. Okay. In fact, what I'll do is I am going to keep this one and then do the absorption on the other line so that you guys can see what we started off with and what we end up with. Yep. So now we move on to the second part, which is phi. So this is what you're given with as the proposed theorem. So the first thing you need to do to that thing is to negate it. So we'll say not phi is the negation of this entire thing. So what do? We gotta we have to take care of the definition of implication first. Okay, so we'll go ahead and do that. So that means, we turn this into an or, but we have to negate the left-hand side of the implication. Are we good so far? Okay. And then look at this, looking at this, I think De Morgan's law makes sense, right? So we will use De Morgan's law. We'll apply to this one first. Now, whether you work from the inside out or outside in, doesn't really matter, okay? It's just a matter of preference. So in this case, I would apply this De Morgan's law, turn this negate in the inside, change the or into an and. And I can do it on this side too, because they are kind of not interfering with each other. So I would, distribute this negation to everything in the inside and then turn the disjunction into a conjunction. So I applied De Morgan's law twice in this case. So if I want to be extra clear that I did it twice, I just say times 2. Are we good so far? Okay. And then what do? We apply De Morgan's law again, or we can do simplification first. Let's do simplification. Okay, so we just say simplify. Okay, now we can apply De Morgan's law again, because this not here, this negation is applied to this particular or, so we can distribute the negation. So we negate everything inside, turn the disjunction into a conjunction, and I will also remove the extra parentheses that we don't need anymore. So this is once again De Morgan's law. Then we have to do another one or two twice. So the next time, the next line is the end of the entire process, because this negation applies to this conjunction. So we just negate everything in the inside and do the same thing over here and turn the conjunction into a disjunction. That's also De Morgan's law. And then the last one is simplification. Simplify. So we take out all the double negation. And there we have it. So are we good so far? So now we make the super CNF, right? So we copy this. Oops. And then we copy this. Okay, I suppose I can do it like this. And then we have to identify what can we do to, try to resolve this. So we look at the not P first, and it looks like it can resolve with this P over here. So that means as a result, we end up with just not R by itself. And then we look at this, not P is all done, okay? There's nothing else I can do with not P. I look at not R, okay? And it can resolve with this R over here. Now I'm doing this in a very systematic way. There may be a faster way to get to the end result here. So I'm just doing this, in an extremely, systematic or procedural way. So we have not P or not Q as a result. Yes.
Because we quickly found not R, can we just collapse all the ones that contain not R?
Yeah, I suppose.
Get rid of P and not R and not Q and not R.
Oh, you're trying to say, can we do absorption?
Or like immediately?
Well, in this test, I did not tell people to use absorption along with resolution. So I'm just going to do this in the purest way, which is resolution only. Yep.
If you do it by hand and use absorption, is it going to like ruin it?
Even okay, what do you mean by ruining it?
Can you still get to 0? Like,
If it could get to 0 originally, then it will still be able to get to 0.
okay.
It does not change the that part. Yep.
If you have not R, wouldn't that technically be not R in 0?
Sorry?
You have not R in 0, wouldn't that be not R in 0? So would that?
I'm not sure what you're
For line 116. Term is not R.
right.
Isn't there like a property where that would also be like not R in 0?
Or 0.
Or 0.
Yeah.
Okay.
Yeah, but I typically don't write the or 0. It's only for clarification where people say, but that doesn't look like a disjunction. I go like, yeah, it is a disjunction. Yep.
I will say that absorption is easier. I actually did it with absorption.
Yeah. Right. So I can change the rules, but in this particular case, the question did not specify anything about absorption. So in your test, I can do so, but since I did not specify that here, I'm going to give you the answer with respect to this question. Yep. So, and I'm going to do it the dumb way, which is going to do all the resolution. So I'm done with this one. Q, not Q, they can resolve, right? These two can resolve. So you can probably see that we are super close to the end result here. Because once these two resolve, I get R back all by itself. So you guys go like, but Tag, look at this not R over here and this R over here. Yes, you can just jump to that conclusion if you choose to ignore all the intermediate steps. Yep. So now the whole thing resolved to a false. Yep.
Last line needed, or could we just say, since R and not R contradict each other, the theorem is proven?
I personally prefer to this to see resolving to a zero. Just so that I know this is the condition why you stop, as a result of the resolution. Yep, go ahead.
Interesting, because like last time we saw this too. We reached a zero, but that's only because we had did it have to be a single variable by itself? Or does it have to just be it has to isolate to a single variable? Because
I'm not sure what the question is. I know what it is about, but I'm not sure about
if we're trying to find a zero, does it have to be a single variable? And the negation of the single variable is the same AND statement.
how else can you get to a zero? Okay, I think I kind of understand your question. So I'm going to pose a question on my own to see if I can answer your question. Okay, so let's just say that we have this, okay? Okay, so the question is, what resolution can you do in this case? Okay, I'll give you two choices. One is you get to false right away. Choice number two is this cannot resolve to false. So which one is it? This one cannot resolve to false. But then someone is going to say, but look at this. P and not P resolves, right? They disappear. And then at the same time, not R also resolves. Can't we resolve two variables at the same time? The answer is no. You choose one as the connection between the two expressions. The rest of the expression can only be concatenated. So you have two choices here. Okay, you have two ways to proceed. Okay, so I'm gonna say way number one. So way number one to proceed is to say, oh, I can use the P to resolve with the not P. So I end up with R or not R, which is basically a one, which is basically saying nothing. So that doesn't buy you anything. Way two is kind of the same thing. So way two is looking at this and say, I would use R and the R, not R, to do the resolution. So you end up with P or not P. P or not P is the same as one. But when you have a one in the conjunction, it doesn't do a single thing. So you just end up with whatever you started off with. So this one cannot resolve to contradiction. Yep.
Okay, so what if we had go back to line 124
Uh-huh.
and then just make the right side the same as the left side, but then put a negation on the outside. So it'd be P or.
But that won't be a CNF anymore.
Okay, but I'm saying if we get it to that.
That is not a CNF.
Right, but if we work it into that, does it count? Because then we could create a variable X that is P or not R.
But you cannot create new variables. Yep. So that's the thing. So the question now is, what if I change this just slightly and I have, this instead? Then it is resolvable, right? Because in this case, you basically just do it step by step. The first thing, I mean, it's up to you to choose which one you want to use first, but since I'm always going from left to right, so I can use this P to resolve with this not P here. Oops, there we go. And then we end up with a not R. Then I can use the R to resolve with the not R. And now we have the false that we want. Is that okay? Does everybody understand, what I'm trying to illustrate here?
So,
Yep.
shouldn't it still work out? Because I'm pretty sure that's just the De Morgan's version of what I was suggesting.
Yes, it
Yeah,
is.
okay. Well, I was just saying, like, can we just look at it and be like, this is negating the
But
same
then you're
thing?
not showing me, that
Okay,
you
so
know
we
how to
gotta work it
perform
out.
resolution, right? So before we get to the CNF, yes, you can use whatever trick you want to get to the CNF. You can simplify the CNF as much as you want using absorption and all the other things.
Then we gotta be present.
And then you have to switch mode to only use resolution. Because the reason why we want to switch to only using resolution is because resolution is extremely mechanical. So it doesn't pay to do any other tricks or simplification, because the machine, you can write a very simple algorithm, like a triple or a quadruple loop at the most, to get this done.
I guess my trouble with the homework was that in the examples you've given us so far in the lectures and things like that, the clauses that you have, each term seems to only have like two variables, whereas the homework had like three or more.
Mhm.
And I was just wondering, is there an example in the practice test or the? test
Nope.
report that
The
doesn't-
practice exam, or all the previous exams only have 3 up to 4 variables. So you don't have the complex, the complex expressions that we did ended up with in the homework assignment. Because in the exam, you only got an hour and 20 minutes. So I cannot give you something that will take like an hour to resolve.
And it's on paper, so we can't copy paste and look between.
Okay, so if you cannot copy and paste, there's still a way to do it, in a very, I can show you how that works. So in this case, okay, I'm gonna use this one as an example. So the way you do it is you express it so that each disjunction is on its own line. Then you can say, line 1 and line 2 resolves, to this line here. And then line 3 and line 4 resolve to a 0. So this way you don't have to rewrite everything that you already have. You only have to work on what is new to the entire conjunction. So using this particular method, you are saving a lot of time by not having to rewrite everything. So, so the whole advantage of copy and paste is pretty much gone. But it also makes it easier for you to explain to me what resolved with what, because you can refer to the line number. You can say line 1 and line 2 resolve to line 3, line 3, line 4 resolve to line 5. Done. So that makes it easy for me also to kind of grade it and go like, okay, you somehow got to a 0, but did you get to the 0 the right way? Yep. Three variables would still be viable, because with 3 variables, the total number of possible disjunctions that you can have is 3 to the power of 3, which is 27. But you cannot end up with 27 because before you end up with 27, you would hit a dead end already. Yep.
So you said from relation all the way up to propositional logic is the test.
Is the scope of this test. Yep. Mhm. So we are running out of time today, which is okay, next Monday to talk about the rest of the exam questions, the non-resolution question. So there are a few questions of non-resolution, which has to do with relations, which also means, this would be a good time for you guys to study, and kind of refresh your memory of relations. So this way you try to do the test at the exam from fall 2022. And then if you have any questions about those things, you can bring those questions to class. Yes. Say that one more time. Yes, your exam 2 from fall 2022 is already up. Are you referring to the one that I'm working on right now, or are you referring to the one that I was? Oh, I see. Yes, that one should be up already. If you go to the announcements. Sorry, I cannot hear you.
Is it possible to put the neutral one?
Yeah, we can do that. Yep.
Yeah.
All right. I will do it right now because if I don't do it now, I am going to forget.
Well, I know about it.
Yeah, I mean,
No,
yeah.
Like, people.
Yeah, yeah.
Yeah.
I get started on it,
I
well,
was like, I got to the end anyway.
yeah.
I was hoping you guys would get so frustrated with the manual process. It's like, I'm gonna write a program to do this.
First reaching my program.
And there's obviously good job, like, maybe there's something wrong.
Yeah, exactly.
And write a program to check, each step of the derivation. Did you guys use a program to check that? Like, when you're deriving the CNF, did you write, some C code just to spot check? Yeah. Yeah. Yeah, because those are all important concepts, when you're employed. If your employer asks you to do something and it's very, very tedious, and then after doing it for 30 minutes, you realize, oh, this is really mechanical. I can just write some code to do it.
Yeah.
Write some code to do it.
Oh, that's a good idea.
All righty, have a nice weekend.
I'm actually curious to know, so for the homework, like you said, the order in which you do resolution matters, so. On my homework, my goal was to find variables by themselves, and so that we, do
Yeah, yeah, yeah.
absorption. So
I get it.
I didn't do it in order, but
No, that's fine. That's totally fine.
so order of resolution. Because like when you said,
If it's resolvable, right, like that one,
yeah,
then you can choose a very clever path, like what you did, and what you did is entirely correct, okay?
Okay.
And you're avoiding a lot of unnecessary steps. But the other one is not resolvable, which means, there's no way you can just kind of
yeah,
shortcut it,
this one right here, yeah, so the same thing, I did it out of order, but at the end.
but you did absorption.
Yes.
Yeah.
And I was able to
Yeah.
get
Yeah, but the class did not know that they were able to use absorption.
yeah,
As a result, I cannot, I mean, I will accept yours, okay, just fine.
Yeah.
But I cannot, I have to grade it based on the assumption that some people did not